Hello, I welcome you all to your own channel MSK Learnium. In this video, we are going to discuss about the thermal stress in composite section. So thermal stress is nothing but the stress induced in a body because of the temperature changes. And composite body means the body which is made up of the more than one material. So we have suppose you have a composite section which is made up of the different two material, let's say brass and steel, right? And when this composite section is subjected to the thermal stress, then what will happen we are going to see. So for that, first of all, we have to draw one composite section body, and I am taking the composite body which is made up of the brass and steel. So here you can go that here I am drawing one section which is the composite section. Okay, so one is the brass and another one is the steel. So here you have this is one composite section, and this section means this is the section which does not induce to the stresses, right? Means it is not subjected to the temperature rise. Now let's say this is the brass, this is your brass, right? And this is the steel. Okay, now so when it is subjected to the temperature changes, means then the thermal stress will induce, and you know that because of the temperature changes this body is going to be elongated, means expansion will take place. Now the material which is made up of the brass and the material which is made up of the steel, whose linear expansion of coefficient is more, that body will be material will be expanded more. So if you know, then the brass is having more linear expansion of coefficient than the steel. So when it is subjected to the temperature changes, that means the brass will expanded more as compared to the steel, right? So the next figure you can say after expansion the body will be like this. So this is your brass and this is the steel, right? If you observe, that means the brass has expanded more and the steel has expanded less. Why? Because the brass is having more linear expansion of coefficient than the steel. So this will be like this. Okay, so let's say this is the brass and this is the steel, right? Now as the brass has expanded more and the steel has expanded less, it means that on the brass we have to apply the compressive force, and on the steel we have to apply the tensile force to make it in the equal length, right? Means the equal expansion. So for that, what I am doing, that I am applying the compressive force on your brass, right? So this is what you are pushing the brass and you are pulling the steel. So this is the second cases. Now the final product you will get like this. This is your final after expansion and after applying the compressive and tensile load on brass and steel, right? So this is how you can see the things. Means simply you can say whenever the composite body is subjected to the temperature rise, the stress will induce. It means that the section is going to be expanded, and the section whose the material whose linear expansion of coefficient is more, that will be expanded more, and the material whose linear expansion is coefficient is less, that will be expanded less. So in this case the brass is expanded more, so we are applying the compressive force or compressive load on the brass and tensile load on the steel. Two conditions you have to satisfy, that load on brass should be equal to the load on steel. Means what? That how much the compressive load you are applying, the same amount of tensile load you have to apply on the tensile load, means on the another body, right? And then you can say the actual expansion of these two materials should be equal. So before that we can write some nomenclature, that let's say that sigma B is the stress in the brass, AB is the area of the brass, Young's modulus, write those. So these things you can write, that let AB is the cross sectional area of brass, right? Sigma B is the stress stress induced in brass, okay, and capital EB is the Young's modulus or modulus of elasticity, Young's modulus of brass, right, of brass, and small eb is the strain in brass, right, small eb is the strain in brass, right. Next you can say alpha b is the linear expansion of coefficient of brass. Alpha b is the linear expansion of coefficient of in brass, right, okay. And lb you can say that is length of brass, right. So now these are the nomenclature for brass. Similarly you can say that similarly, right, that is as comma sigma s comma es comma small es comma alpha s comma ls, corresponding values for what? For steel, values for steel, okay. Now then you can say two equation you have to satisfy, that is load on that is compressive load on brass is equal to tensile load on steel. Why compressive? Why? Because you have applied the compressive load here right now. So you can say that, just hold on, yes. So next we can say, we have a page right now, so don't waste. So now you can write that compressive load on brass is equal to, this is continuation, that is tensile load on steel is equal to tensile load on steel, okay. So load is what? Load is nothing but the stress into area. So as we have a compressive load on brass is nothing but, you can say sigma b into ab, stress into area is the load, is equal to sigma s into as. From this you can get the relation between sigma b and as. So what is that? You can say like this, sigma b is equal to sigma s times of as by ab, is it? So this is one relation you got which is useful for finding the stresses in the different material, okay, while solving the numerical problem. So next we have to satisfy one more equation that we can say, that is actual expansion in brass is equal to actual expansion in steel. So next you can write that, here we go, see, you can write actual expansion in brass is equal to actual expansion in steel. See, as I have taken one example that composite section is made up of the brass and steel, right? So it's not like that always you will get the brass and steel only. Any two different material you can get which is made up which is the section of a composite right now. So now you need to find out the actual expansion in steel. So I'll show you the figure that actual expansion of brass and steel is what? Actual expansion is nothing but, first of all, because of their linear properties, means because of the thermal expansion of coefficient, the brass has expanded itself, right, by because of the thermal change, temperature rise, right, and also the steel has expanded by self, okay, means there is some expansion in both the material because of its own material properties, right. And then we have additionally, means we can compress on the brass and we are tensile the steel, right. So you can say the actual expansion of steel is what? That is, if I talk about the brass, it means that free expansion of brass minus compressive strain, contraction due to the compressive load, right? So now you can say that if I write down the actual expansion in brass, right? Actual expansion in brass. So what is that? That you can write free expansion in brass, right, minus free expansion means what? Because of the linear expansion of coefficient and temperature rises, the brass has expanded, minus contraction. Why? Because we are compressive, right? We have to reduce the length, contraction due to compressive load, right? Due to compressive load. Is it? Now, so a free expansion formula is what? Expansion is nothing but the alpha TL, right? So you can say alpha B into TLB, and contraction due to compressive load is what? You know that, remember that sigma B by EB into LB, right? That is delta L is what? Delta L is nothing but the strain into length. So strain is what? Sigma by E, and the length is L. Got it? So let's say this is equation 1, right? Next you can say the actual expansion in steel. So here that expansion in steel means what? The steel has expanded by itself because of the temperature rise, and then we are applying the tensile load, means we are pulling this, means we are increasing the length. So here we have a extension in steel due to tensile load. So you can write next, that is actual expansion in where? In steel, right? So what is that? You can say free expansion in steel plus expansion, that is extension due to tensile load, right? Due to tensile load. So free expansion in steel is what? That you can say alpha S T into LS plus sigma S by ES into LS. Let's say this is equation 2. Now you know the actual expansion in brass is equal to actual expansion in steel. So you can equate them, right? So when you equate, that equation will become like this, that equating, you can say equating 1 and 2, right? So when we equate 1 and 2, it means this will be the alpha B TLB minus sigma B by EB into LB is equal to alpha S TLS plus sigma S by ES into LS. So length of the brass and steel are equal, so we can cancel them, right? So we are cancelling them, this and this. So the equation will be like this, that is you can say alpha B into T minus sigma B by EB is equal to alpha S into T plus sigma S by ES, right? By using this you can get the stresses in the different material, or whatever the data they want to know, you can find by using the first relation which we got, the load on this, that is sigma B and sigma S relation we already calculated. We will put in this equation and we'll get the required values, right? So this is what, whenever the body is subjected to the thermal stress, specifically composite section, we have to use this relation, means load on the two bodies will be equal and actual expansion in two bodies will be equal. We have to see which body is which material is expanded more, because of, by looking there linear expansion of coefficient, right? And then we can apply the compressive and tensile load. So now based on that we will solve one numerical problem and then see how can we implement this thermal stress analysis in a numerical problems. So let's see that the problem is on the screen. Wait. So you have one problem, please write down. The steel tube of 30 mm external diameter and 20 mm internal diameter encloses a copper rod of 15 mm diameter. So you have a steel tube is there, right, which is hollow, whose outer diameter is 30 and inner diameter is 20, and in this the copper rod is inserted. So the steel and copper, it means that it is the composite section, right, to which it is rigidly joined at each end. If at a temperature of 10 degrees centigrade there is no longitudinal stresses, calculate the stress in the rod and tube when the temperature is raised to 200 degrees centigrade. Take Young's modulus for a steel, that is ES is 2.1 into 10 to the power 5 Newton per mm square, and for copper 1 into 10 to the power 5 Newton per mm square. Then alpha S means linear expansion of coefficient for a steel is 11 into 10 to the power minus 6 per degree centigrade, and alpha C means linear expansion of coefficient for copper is 18 into 10 to the power minus 6. So you have a simply you can say, means you have a steel tube is there whose external diameter is 30 and internal is 20. Inside the steel tube that copper rod is inserted whose diameter is 50, and these two are fixed at two ends, right, and they are subjected to 10 degrees centigrade. There is no longitudinal stress, right. Calculate the stresses in the rod, means sigma S and sigma C you have to calculate when the temperature is reached to 200 degrees centigrade, right. So you have to steel properties and copper properties is given. So now what is that? This is the composite section, and this composite body is subjected to the temperature rise, right. It means that the thermal stress in composite section we have, right. So we will use the concept of thermal stress in composite section, and then we can find out the stresses. So first of all, if I draw this, that let's say you have a one steel tube like this, is it or not? So this is your, suppose this is your outer diameter and this is the inner diameter, right. This, let me locate this center. So this is your 30 mm, right, and this is your 15 mm, sorry, 20 mm. This is a steel only, right, 20 mm. Inside this you have a one copper rod is there whose diameter is 15 is given, okay. This is the 15. So if I show you with different color, it means this red color is about the steel inner diameter, and this black one, I think this black one is for your copper, right, and this one is the outer diameter of the steel. So now you can write down the given data, that given data, what, that is D naught is equal to 30 millimeter, right, DI is equal to 20 millimeter, right. Here I am writing not I means, but while I'll find the area I can use the A's, right, and DC, that is diameter of the copper rod, is 15 mm, right, and the temperature rise is given, that is, if you see that T is equal to 200, initially it was 10 degrees centigrade and there is no longitudinal stresses. Calculate the stress in the rod and tube when the temperature is raised to 200 degrees centigrade. So if I see the temperature change is what, that is 200 minus 10 means 190 degree centigrade, right. This much of temperature is raised from 10 to 200. Now the properties of steel and copper is given, Young's modulus for steel and copper is given, that also you can write, no problem. So here itself, that ES is equal to 2.1 into 10 to the power 5 and alpha S is equal to 11 into 10 to the power minus 6 per degree centigrade, and EB is equal to this is 1 into 10 to the power 5 Newton per mm square, and alpha B is equal to 18 into 10 to the power minus 6 per degree centigrade. I'll tell you that if you look at the values for linear expansion of coefficient for steel and brass is having linear expansion of coefficient is 18 into 10 to the power minus 6 and steel is having 11 into 10 to the power minus 6, which means that brass will be expanded more than the steel. So while you do the calculation, means while you put the condition for the thermal stress in composite body, then brass will be subjected to the compressive load and the steel will subjected to the tensile load. Means steel is expanded less than the brass. Okay, so now here first of all what we are going to find, that area of the steel and area of the copper rod we can find right now. So now I can say, let's say AS is the area of steel, right? It is what? Pi by 4, d naught square means 30 square minus 20 square. We'll get some values. So very fast. So you got this 392.69, right? 392.69 millimeter square, right? And then area of brass, that is copper, is what? Pi by 4 into d square, that d is 15 square. So you have a so it is 176.71 mm square. Okay, now we have to say the load on steel is equal to load on copper, but copper is subjected to the compressive. So you can say the compressive load on brass is equal to tensile load on steel. Why steel is tensile? Why? Because steel has a linear expansion of coefficient is less, so it will be expanded more, means we have to pull the steel, but we have to compress the brass, right? And tensile load on where? On steel. So this is what? Sigma b into that is sigma b into AB is equal to, brass is nothing but the copper, that is sigma c, you can write sigma c into AC. This is copper, right? Otherwise the people will get confused. That is sigma s into AS. Okay, so now you can get sigma c and sigma s relation, that sigma c is equal to sigma s times of AS by AC, that is AS by AC, right? This is C and this is C. So you have a sigma c is equal to sigma s into AS is what? AS is got 392.69 392.69 by 176.71, right? So you will get 392.69 divided by 176.71. So 2.22. It means you can say the stress on copper is equal to 2.22 times of stress in steel. First relation we got, right? Now what we have to do, we have to say the actual expansion of steel is equal to actual expansion of brass, right? So first of all I am finding the actual expansion of brass and actual expansion of steel, and then we can equate. Okay, so you can say here that next you have a actual expansion in where? In brass, in copper, right? In copper. So actual expansion in copper is what? Free expansion in copper, right? In copper minus contraction due to compressive load, right? Due to compressive load. And what is the value? That you can say free expansion is nothing but the alpha c T into LC, right? Minus sigma c by EC into LC. This is equation 1. Then you can find the actual expansion in steel, right? So now you can write, that is second actual actual expansion in where? In your steel, right? So that is nothing but the free expansion in a steel plus expansion due to what? Due to tensile load, right? So free expansion is what? That is alpha s T into Ls plus sigma s by Es into Ls. This is equation 2. Expansion due to tensile load, right? We can equate 1 and 2. So you can say, you can write it here that equating 1 and 2. Right now, so we can say equating 1 and 2. So when you equate 1 and 2, that equation 1 is nothing but the alpha c T into Lc minus sigma c by Ec into Lc is equal to alpha s T into Ls plus sigma s by Es into Ls. But you know the length in both the body will be same, so this Ls Lc will get cancelled. The equation is become like this, that is alpha c into T minus sigma c by Ec, right, is equal to alpha s into T plus sigma s by Es. So we'll put the values. Alpha c is nothing but the 18 into 10 to the power of minus 6 and T is 190 minus sigma c is equal to, I can write 2.22 times of sigma s, which we have calculated, and Ec is 1 into 10 to the power of 5. Let me check. Yes, so 1 into 10 to the power of 5, right? That is equal to alpha s. Alpha s is 11. Yes, 11 into 10 to the power of minus 6, right? And T is what? 190. That is continuation plus sigma s. Sigma s is sigma s only, and Es is 2.1 into 10 to the power of 5. This data is given to you. We have simply substituted those data, whatever the data is given in our questions, right? Now you can say here, see, this term will come this side and this term will be another side. So we can write it here, that is, sorry. So you can do one thing, that make a simplification, 18 into 10 to the power of minus 6 into 190 minus 11 into 10 to the power of minus 6 into 190. This will become this side, and that is equal to continuation. This is equal to sigma s, right, by 2.1 into 10 to the power of 5. This minus will come to this side, it will become plus, that is 2.22 sigma s by 1 into 10 to the power of 5, right? So on simplification, I'll show you that directly. That, let me do that. 7 into 10 to the power of minus 6 into 190. So this will come like this, that is 1 point, this term will become 1.33 into 10 to the power of minus 3, that is, and sigma s you will get common, so it will be 1 by 2.1 into 10 to the power of 5, right, plus 2.22 by 10 to the power of 5. So that is 2.696 into 10 to the power minus 5. So this will be 2.696 into 10 to the power of minus 5 sigma s, right? So sigma s we already calculated, which is 1.33 into 10 to the power of minus 3 by 2.696 into 10 to the power of minus 5, right? So sigma s we calculated, means it will be 1.33 into 10 to the power of minus 3 by 2.696 into 10 to the power of minus 5. So you have a sigma s is equal to 49.33 Newton per mm square, right? And sigma c is equal to 2.22 times of this, so you can simply answer into 2.22. this is what 109.51 Newton per mm square. So we got that stresses in steel and stresses in copper is this one. So this is how we can solve the problem when the problem is subjected to the thermal stress and for the composite section. So this is all about the today class. Please do like, subscribe and share this channel with your friends. Thank you.